Hello, my lovely students. In this lesson, we will be rounding out our understanding of velocity and acceleration by finally introducing some equations and walking through some examples of how we can use those equations to predict an object's motion. So let's dive in. So as a reminder, we've got two big categories of motion. There's constant velocity motion, where an object maintains a constant speed, constant direction, isn't accelerating in any way. And then the alternative is accelerated motion, where an object is speeding up or slowing down or changing direction in some way. So we'll discuss each of these different categories separately because they require slightly different thinking. So for constant velocity, we previously discovered that if we have an object moving at constant velocity and we gather data about its displacement at different time intervals, and then we make that graph and we do our best fit line, we find a linear relationship between displacement and time for that constant velocity object. And so the general form of that best fit line looks something like the equation you see here. Displacement equals some constant produced by our computer determining the best fit line multiplied by the time. But we've kind of glossed over so far exactly what that constant means. We've kind of danced around it. So let's go ahead and just dive in a little bit deeper. So if we rearrange this equation to solve for that constant, we divide both sides of the equation by time. And so that gives us that this constant that was produced by Desmos or whatever curve fitting software you're using is equal to displacement divided by time. Well, displacement divided by time, that rate we've already defined previously as velocity. So what this equation is really telling us, the best fit line from this graph is just giving us the equation that displacement is equal to velocity times time. And so that's our first equation that we are dealing with here. The displacement is equal to our velocity if it's constant. If it's changing a little bit, then whatever the average velocity, the overall velocity multiplied by time. Or we can rearrange that, if it's easier to think about it, is that our average velocity for a given motion is equal to the total displacement for the entire journey divided by the total amount of time that the journey took. And so I've defined for you here what each of those variables mean in this equation, as well as the units that we typically use for them. So displacement is represented by either delta x, which again represents change in position, or we can just use the variable d for displacement. We typically measure that in meters, but we could use miles, feet, kilometers, any other measurement that kind of shows how long or how far something is. Right? The next variable is v or v-av. We do the little subscript there to indicate average velocity. And so if it's changing, we can find the average by just dividing displacement by time, or if it's constant velocity, we just plug that in right there. Typically measured in meters per second, but could be miles per hour, feet per year, like whatever. And then T is for time, which we typically measure in seconds. All right, so now let's dive over into acceleration instead. Now, we established before that displacement and time are quadratically related for an accelerating object. Or in other words, if I collect data about its displacement as a function of its time and do that curve fit, I find that my data points tend to follow a parabola, essentially. So then that gives us the equation of displacement is equal to some constant produced by our curve fitting software multiplied by time squared. So this is the equivalent of y equals ax squared, but just in physics language instead here. Okay. So again, we got this constant that tells us something about the steepness of the parabola, but it also has some other physical meaning as well, which we got a chance to dive into a little bit earlier in class, that if we really examine that constant and compare it to our data, what we find is that the constant in our line of best fit is equal to half of the object's acceleration, the rate at which its velocity is changing. So what that means is that our best fit line for our displacement versus time graph is just really showing us that displacement equals 1/2 of the acceleration multiplied by time squared. That's the whole thing. And so we were able to just just derive our very own formula for accelerating objects. So, that's cute. And so this works fine as long as our object starts from rest and then continues to maintain a constant acceleration. If our object does not start from rest, or if we have other information available to us or what have you, it can be helpful to have a slightly more comprehensive set of equations. And so I bequeath unto you our acceleration equations, 4 formulas that allow you to analyze the motion of an object that is accelerating. All right, now this looks like a bunch here, but the key thing that I want you to notice is that all of these can be used to describe a situation where an object is accelerating. The difference is just which variables are included. And so which equation you use is just going to depend on what information you're given in the problem and what it is that you are trying to solve for, okay? So it's not like, they mean fundamentally different things. All of these describe the motion of an object that is accelerating at a consistent rate. But which one you use will just depend on what information you're working with here, okay? So 5 different variables that can show up in here. D is for displacement. And then now that our velocity is changing, it's not enough to just say V, because it depends on, well, when is that the velocity? Is that the velocity at the beginning of the time that the object is accelerating? Is that its ending velocity? And so now we have to specify when the object has that particular velocity. So we would use V with a subscript I to indicate initial velocity at the start of the accelerating period. And then VF would indicate final velocity, the velocity at the end of the acceleration. Both of those tend to be measured in meters per second for our purposes. We're now introducing A as well for acceleration. And again, acceleration describes a change in velocity over time. So then our units for acceleration will be some unit of velocity, like meters per second, divided by some unit of time, like seconds. So meters per second, or we could write that as meters per second squared, or it could be a number of other things. It could be feet per second per year. As long as you've got a unit of velocity divided by a unit of time, it works okay as a unit for acceleration to measure that. And then of course, T is for time, measured in seconds. So again, we've got 5 different variables that could show up in our acceleration equations, and each of these formulas only includes 4 of those 5. So depending on which variables you have in a particular problem, you'll choose whichever equation best matches the variables that you have and that you are looking for. We'll work through a couple examples of that in just a moment. First, I really want to kind of unpack these equations for you and explain where they came from, because I just sort of like plopped them in your lap, but they really do kind of intuitively make sense as well if we know what to look for. So let's just unpack that really quickly. All right. So our first equation, D equals 1/2 times the sum of initial plus final velocity multiplied by time. Now, if we have 1/2 of the initial velocity plus the final velocity for a consistently accelerating object, an object that has its velocity changing at a constant rate, when we do that, 1/2 of the sum of the initial and final velocity, that's just the average velocity, right? This is sort of our basic average velocity calculation there. And so we can rewrite this equation as displacement is equal to average velocity times time. Well, that was what we saw right at the beginning when we were talking about constant velocity. So this is the same thing, just expanded out for an accelerating object. Okay? Second equation is that final velocity is equal to initial velocity plus acceleration times time. So I'm going to go ahead and rearrange this equation a little bit. So I'm going to subtract initial velocity from both sides. So then that becomes final velocity minus initial velocity equals acceleration times time. And then if I divide both sides by time, I get VF minus VI over time is equal to acceleration. Now that may look kind of weird, like why did I do that? Like that looks so much uglier than the other version that I just saw. But if I think about this a little bit more, VF minus VI, that's the change in velocity. And so this really just means change in velocity over time. That's our definition of acceleration. So basically this equation just falls out of the definition of acceleration as rate of change in velocity over time. We just rearranged the equation a little bit to get rid of the fraction and make it look a little bit prettier, right? But ultimately, that's all that this equation is. Now our third equation should look a little bit familiar because we pulled this from our graph. So that 1/2 at squared part, that came from our quadratic graph that we saw before. So we had just figured that out from the graph itself and from doing our data collection and applying our best fit line. Now there's a little extra term out in front because again, the whole d equals 1/2 at squared only really works if we're starting from rest. If we're not starting from rest, then our object has a little bit of an extra boost. It's going to get a little bit farther because it wasn't starting from zero. It started with a velocity already. And so we can kind of calculate that little extra boost using our equation of displacement equals velocity times time. So we would just use whatever the initial velocity is to tell us sort of what that initial boost was. So that gives us then an overall comprehensive equation of displacement equals initial velocity times time plus 1/2 times the acceleration times time squared. And then there's a fourth equation, final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. I don't really have like a cute little thing to show you about like this makes so much sense. But basically it sort of arises from combining the other equations and sort of rearranging and canceling things out and solving for something different. The other thing is that equation 4 actually will make a lot more sense once we talk about energy. It sort of naturally arises out of the concept of energy conservation. But again, that's for a later unit, so we're going to save that idea and table it for now. All right, so now we've got all these equations, all these formulas at our disposal that we can use to analyze the world. But sometimes it can be a little overwhelming in a physics problem to figure out, well, what am I doing? Like, what do I know? What do I not know? Which of these equations am I using? I went from no equations to now I've got like 5. What is going on? And so my recommendation is that you guess. Where by guess, I don't mean like take a shot in the dark. I mean, I guess you could if you really had to, but that's not really the most proven method. But instead, guess is our acronym to kind of walk us through a great process to use to figure out how to solve a physics problem. So the G stands for given. So you go through, comb through the problem statement and identify what are all the pieces of information given to me? What are all the numbers or the implied numbers given in my problem? Making sure to list out for yourself not only the numbers, but also the variables that they represent and the units that they're measured in. This is going to be important. Okay. The U stands for unknown. So what is it that you're trying to solve for? What's the goal of this problem? And again, make sure that you are identifying that variable that you're solving for. E stands for equation. So once you've got your list of all the variables of interest, all the information that you know, and the thing that you're trying to solve for, you can go through and look for a formula that includes all of those different components. And so therefore, which equation is going to be most useful to you to make those connections. All right. The first S, I kind of cheated and put 2 S's in one. It's substitute and solve. So substitute in your values from the givens and unknowns into the equation that you identified in the third step, and then go ahead and rearrange as needed, do a little arithmetic, a little algebra, and solve for your unknown variable. My final S stands for sense making. So at the very end, I like to do a little bit of a reality check and say, does this answer make sense? Does it seem reasonable given the situation? So if I calculate that, a car is accelerating down the freeway and is ultimately after, hitting the accelerator for, 30 seconds or whatever, I calculate that it's going like 0.002 meters per second. Like that's weird. That doesn't make sense. That shouldn't be happening. All right. So we do a final just check to say like, does this seem reasonable for the situation? So let's walk through an example. All right. So say we've got a gazelle that is accelerating uniformly from rest and travels 21.4 meters over the course of 6.5 seconds. And we want to figure out how fast the gazelle is moving at the end of this time period. So we start with G, our givens. What information is given to us? And sometimes it's numbers that are explicitly laid out. Sometimes it's numbers that we have to kind of interpret are there. All right. So some of the things that I'm seeing in here are the gazelle starts at rest. At rest means it's not moving. Not moving means velocity is 0. All right. Now the gazelle doesn't stay at a velocity of 0. This would be a very boring problem. if it did, but it starts at 0. So that tells me that for this time period, the initial velocity, the starting velocity, is 0 because my gazelle started from rest. I also know that it traveled 21.4 meters, so that's the displacement. That's how far it went. I can also tell because the units are meters, and meters are a unit of displacement. And then my time is 6.5 seconds. Good. So this is all the information that is given to me. If I'm figuring out my unknown, what am I trying to solve for? It's how fast is it moving at the end. How fast indicates a velocity, and then at the end indicates that we're trying to solve for our final velocity for all of this. Okay, so what I do now is I look through and I say, okay, all the variables that I've identified are VI, D, T, and VF. So I've got my gazelle is accelerating, so I want an acceleration equation, and I want to make sure it has those 4 variables. So which equation should I use? The good news is there is only one formula out of those 4 that has those 4 variables, and that equation is displacement equals 1/2 times VI plus VF times T. Now I know it's going to be tempting to choose one of the equations that has VF all by itself on one side of the equals sign, but neither of those ones is going to work because both of them require me to know the acceleration, and I don't know the acceleration here. It's better to go with this equation because it has all of my variables. I can always rearrange it to solve for final velocity. Okay, so now I'm going to go ahead and substitute things in and solve. So that gives me 21.4 meters is equal to 1/2 times 0 plus final velocity times 6.5 seconds. Now I can multiply any of those quantities on the right in any order I want. That's the commutative principle. And so I'm going to multiply 1/2 times 6.5, which becomes 3.25, multiplied by VF. I can get rid of the plus 0 because plus 0 doesn't do anything. And then I go ahead and divide both sides by 3.25, gives me a final velocity of 6.58 meters per second. Now, does this make sense? 6.58 meters per second is about a little under 15 miles per hour. So that's speedy, but I would expect a gazelle to be able to go pretty fast in order to, not be lunch for a lion or whatever. So it seems within the realm of reasonable to me. If it were going like 100 miles per hour, I'd be wary. But this seems like a reasonable number to me. All right, let's go through and check your understanding now. So first part of this problem is that a motorcyclist is traveling at 15 meters per second. How long is it going to take him to travel 250 meters? All right, so walking through this problem, here's what I know. I know that the velocity is 15 meters per second. It doesn't say anything about the velocity changing. There's no speeding up, there's no slowing down. So that's just the velocity. No need to put initial or final on it. That's just what it is, all right? And then my displacement is 250 meters. I am trying to solve for the amount of time that this is taking. Right, so since my motorcyclist is moving at a constant velocity, there's really only one equation, which is that displacement equals velocity times time. So I can go ahead and plug everything in there, divide both sides by that velocity of 15 meters per second, and that gives me a time of a little under 17 seconds, so 16.67 seconds. Now, does that make sense? Well, 250 meters is about 820 feet. All right, and then 15 meters per second, that's about 34 miles per hour. So kind of doing those modifications, those conversions, kind of helps us to evaluate a little bit more using language that we're used to because, alas, America doesn't use the metric system. All right, so anyway, so given that we're moving 34 miles per hour, we're talking about 820 feet there, about 17 seconds to cross that seems reasonable to me. So I'll take it. Cool. All right. So second part of this problem is that our motorcyclist, which is still moving along at 15 meters per second, sees a stop sign, hits the brakes, accelerates at -3 meters per second squared. How long is it going to take this motorcyclist to come to a stop? We're walking through this one. Again, I'm going to go through and identify what's my given information. So my motorcyclist is at the beginning of this story moving at 15 meters per second and then hits the brakes and causes this acceleration. So the initial velocity is the 15 meters per second. At the beginning of the acceleration is -3 meters per second. And then the other key piece of information in here is that the motorcyclist is trying to come to a stop. Since the motorcyclist is coming to a stop, my expectation is that the final velocity is 0, because he's not moving anymore at that point. So those are my given information here. It's asking how long it's going to take for him to come to a stop. So that means I am solving for time. So now I'm looking for an equation then that has initial velocity, acceleration, final velocity, and time. So the one equation that has all of those is that final velocity equals initial velocity plus acceleration times time. Right? So now I just go ahead and plug everything in here, and then I just do a little algebra to rearrange. So going in reverse PEMDAS order, I'm going to subtract my 15 meters per second first, and then I'll go through and divide both sides by -3 in order to undo that multiplication. This gives me a stopping time of 5 seconds. And if we're starting off at about 34 miles per hour, taking 5 seconds to come to a stop, that seems like a reasonable amount of time based on my own experiences driving. So that is it. So now you've got all these equations at your disposal to help you numerically, computationally analyze different types of motion. So go forth, do physics, be brilliant.